Up to this point, we've used the natural deduction proof method to show how a conclusion can be proved from a set of premises. In this lesson, we're going to cover a few additional concepts that can be proven with this natural deduction system. These proof-theoretic concepts are going to apply to single sentences, pairs of sentences, and a few sets of sentences. That might sound familiar, but it's important to differentiate these proof-theoretic concepts from the semantic concepts that we covered in lesson 4.2. And not in this video, but the next one, we'll cover the relationship between those semantic concepts we covered previously and the proof-theoretic concepts we're about to look at now. So we have a simple goal in this lesson to learn how to construct proofs to show the following: that a sentence is a theorem, that a pair of sentences are provably equivalent, and that a set of sentences are provably inconsistent. And for each of these concepts, we're going to look at a definition and how to correctly use proofs to show them, and then look at an example. A theorem is a sentence of truth functional logic that can be proved from no assumptions at all. What does that mean? In order to prove that a sentence is a theorem, we have to always start with some subproof, since we're not starting with assumptions to work from. That gives us the following strategy for proving a theorem. It might be good to write the theorem down at the bottom of your empty proof as a goal that you're working towards. Then you need to be guided by the main connective of a theorem in constructing the rest of your proof. So for example, if the main connective of the theorem is a conditional or a biconditional or a negation, each of those are subproof rules for introducing those connectives. So you start with the assumption relevant to those subproofs. If the main connective of your theorem is a conjunction, the conjunction introduction rule is simple, but you'll need to figure out how to introduce each of the conjuncts. And if the main connective of the theorem is a disjunction, or those other starting strategies get you stuck, your best bet might be to try an indirect proof. Here's our example of a theorem of truth functional logic. You'll notice it's going to be quite a complex sentence, and I've set up the basic structure of the proof already by putting this sentence at the end. And then the next step in our strategy was to identify the main connective. So it can be a little bit tricky with all of these parentheses and various connectives. But here we have an or that links to simple statements P and Q. And then that seems to be the antecedent for this conditional, which has not R as its consequent. And that all falls within these parentheses. And that's the antecedent to this conditional. And this negated conjunction is in the consequent. So this is our main connective. And I'll color it in red for you. Since our main connective is a conditional, we're going to need to run a conditional introduction by assuming the antecedent and then trying to prove the consequent. So now we have the basic structure of our conditional introduction rule with the antecedent as our assumption, and we should be able to prove this consequent. Now we need to figure out what comes after this first assumption to allow us to prove that consequent. Since the consequent we're trying to assume is a negated sentence, that suggests that a good strategy might be to try negation introduction. So we have to write the negation of that sentence and try to prove a contradiction. So here's the non-negated sentence, R and P, and we're trying to get not R and P eventually by getting a contradiction at this line. And that will allow us to introduce not R and P by indirect proof, lines 2 to whatever this one with the contradiction is. Now we have a sentence that we can apply non-subproof rules to at line 2, so we should do that. Now we have R on line 3 and P on line 4, both of which are justified by conjunction elimination applied to line 2. The other assumption we have to work with is the one at line 1. We want to see if we can use that conditional at line 1 to see if it helps us get to a contradiction. So can we generate the antecedent to that conditional from what we have? The antecedent is P or Q, and we can get that because we have P and a rule for disjunction introduction. So that gives us P or Q on line 5, justified by disjunction introduction on line 4. And now we can apply conditional elimination to get not R on line 6. So line 5 has the antecedent of the conditional, and so we can write the consequent of the conditional on line 1, not R, down there on line 6. And since we have R on line 3 and not R on line 6, that allows us to infer the contradiction that we were hoping to all along. At this point, actually, our proof is complete. All we have to do is fill in our justifications on line numbers. So line 7 is justified by negation elimination. That's the rule that allows us to introduce that symbol for contradiction. And we apply it to lines 3 and 6, where we have a sentence and its negation. Line 8 comes from our negation introduction subproof that started at line 2. And since we assumed R and P and proved a contradiction, that shows us that not R and P can be added to that second subproof. And finally, since we have the antecedent assumed at line 1 and then proved the consequent, that means we can add the initial conditional that we were hoping for at line 9, and we've proved this sentence from no assumptions at all, making it a theorem of truth functional logic. The next proof-theoretic property that we're going to consider is called provable equivalence. And this is when two sentences of truth functional logic can each be proved from the other. This means that to prove equivalence, we need two proofs. So we have two sentences, 1 and 2. The first takes sentence 1 as an assumption and proves sentence 2. The other proof takes sentence 2 as an assumption and proves sentence 1. You can't prove equivalence without two proofs. To demonstrate provable equivalence, I have what turned out to be quite a complex pair of examples. The main thing to know is that here we have two sentences, P if and only if not Q, and it's not the case that P if and only if Q. To show that these are provably equivalent, we start by assuming one sentence and proving the other, and that's in the first proof. And then in a second proof, we start by assuming the other sentence and proving the one that was our assumption in the first proof. So notice here, our first line is P if and only if not Q, and we're going to prove it's not the case that P if and only if Q. And here, P if and only if not Q is what we're trying to prove from it's not the case that P if and only if Q. For this first proof, my conclusion needs to be the negation of a biconditional. We don't have a rule that allows us to introduce a negated biconditional in particular, but we do have a rule that allows us to introduce a negated sentence. And that's if we assume the sentence, prove a contradiction, then we can get its negation. You've seen that before. So here, since we have to get it's not the case that P if and only if Q, we need to start by assuming P if and only if Q and seeing if that allows us to prove a contradiction. That along with the sentence that we started by assuming. To close this negation introduction, we need to get within this subproof some sentence and its negation. That will likely be P on a line and not P on another line, or Q on a line and not Q on a line. The strategy I've decided to try is to start by assuming P and seeing if I can prove not P, and then I'm going to try a secondary subproof at the same level and seeing if I can assume not P and prove P. That will allow me to get a contradiction at this level and then the negation of this sentence. So this will be the overall structure of my proof. Within this, I'm going to try and prove the negation of P and Q, which is my endpoint conclusion. And I'm going to get that because this is a negation introduction proof. So I'm hoping to prove a contradiction. And I'm hoping to get that by getting not P after one subproof and P after another. The reason I chose these is it looked like I could maybe, by starting with P, get not Q and Q, and easily get not P, and then figure out what to do within this one to get another contradiction and add P to my proof. So I did two things. First, I tried looking ahead to figure out a strategy that might let me get the conclusion. That got me this mid-level subproof. And then for these furthest in subproofs, I just wanted to see if I could generate the contradiction necessary to finish up this main subproof. So what I said was I thought I could get Q and not Q by assuming P. And that's by applying biconditional elimination, using 3 on 1 and 2. That allows me to generate a contradiction, which is what I need to close my negation introduction subproof. So because lines 4 and 5 allow me to prove a contradiction at line 6, I've completed what I need to for negation introduction, so that closes the subproof that goes from lines 3 to 6, and I can add not P within this wider subproof. Now I can move on to my next subproof starting at line 8, where by indirect proof I assume not P and see if I can prove a contradiction so that I can add P outside this narrower subproof. To close an indirect proof, I need to end with a contradiction, so I'm probably going to either need to get not P and P within this subproof, or I'm going to need to get Q and not Q within it. Now, I did something kind of funny at line 9 here. I made another assumption of not Q. Why would I do this? Well, I need a way to get P, I'm hoping, out of this first conditional. You could just as easily have assumed Q and used the second biconditional. Either of those would have allowed you to infer P. But if I have if not Q, then P, and I have not P, that allows me to apply modus tollens. And I'm hoping that that gets me some contradiction out of these initial two assumptions. So I've introduced here a conditional with this short little subproof. And if I have if not Q, then P, and I have not P, I can use modus tollens to get the next line. So applying modus tollens to 11 gives me not Q. I also need to reference line 8 there, since that was where the negation of the consequent was. And then I can apply double negation elimination to 12 to get just Q. Well, since I have Q, I can apply biconditional elimination with Q applied to line 2 to give me the sentence P on line 14. Now within this subproof, I have not P and P, which gives me a contradiction. And adding a contradiction is always justified by negation elimination. And then because I've arrived at a contradiction, that's how I close a subproof for indirect proof. That allows me to add the sentence P at line 16. So that spans the length of the indirect proof, which was starting at line 8 and going through line 15. And now at this middle layer, I have not P at 7 and P at 16. So that means I've proved a contradiction at this layer too. Since I've proved a contradiction by assuming the sentence P if and only if Q, that means that I can add not P if and only if Q to the end of my proof, which was the sentence I was aiming for all along. Now, I said this is a complex example. That is only one direction of the equivalence proof. Now we have to assume this sentence at the end and prove the one that's at the beginning. So we have to do the proof in reverse. For proving this direction of the equivalence, we're starting with the negation of P if and only if Q, and we're trying to prove a biconditional. There's no rule that we can immediately apply to our assumption because it's a negated sentence. And we don't have a negation elimination rule without finding the negation of that sentence or the sentence P if and only if Q. So we can't apply anything just to our assumption. That means we're going to have to look for our conclusion. For where to go next, our conclusion is a biconditional, and that suggests we're going to have to use our biconditional introduction rule. Biconditional introduction requires two subproofs, one where we start with P and prove not Q, the other where we start with not Q and prove P. So here I've marked the basic structure of our proof. One subproof where we start with P as an assumption for biconditional introduction and prove not Q, the other where we start with not Q as another assumption for biconditional introduction and prove P, and those two subproofs together are going to justify biconditional introduction of our conclusion on whatever this last line is. So the tricky part is going to be to figure out how, with this assumption, to prove not Q from P and P from not Q. It turns out that the way to do it is with a lot of subproofs within subproofs. For this first subproof, since my last line is not Q, that's a negated sentence, so I'm going to start with negation introduction. Negation introduction has me start with Q and try to prove a contradiction. To prove a contradiction, I'm either going to need to find not P to contradict this sentence, or I'm going to need to find P if and only if Q to contradict this sentence. When I look at these, I think it's more likely that I'll be able to get the sentence P if and only if Q, because there's got to be some way that I have to use that assumption to justify my conclusion. So likely by assuming Q, I'm going to be able to prove P if and only if Q. Since I have P and Q already as assumptions on my tree, I can actually do something funny with two little subproofs. If I assume Q again, I can prove P, and if I assume P again, I can prove Q. With these two subproofs, if Q then P and if P then Q, that allows me to add the biconditional P if and only if Q outside of these two subproofs. So both of these were introduced for biconditional introduction. The biconditional I've introduced here at line 8, its negation appears at line 1. So that justifies the contradiction I was hoping for at the end of this subproof. By assuming Q, I was able to prove a contradiction that allowed me to add not Q to this first subproof. So I've got one direction of the biconditional in my conclusion already proved. So that was negation introduction, lines 3 to 9. And eventually, I'm going to justify the first direction of the biconditional with lines 2 to 10 at the concluding line. Now at line 11, I need to assume not Q and see if I can prove P. To get P as the end of this subproof, I'm going to start another subproof. That's an indirect proof. So I'm going to try assuming not P, showing that that leads to a contradiction, and by the indirect proof rule, that would allow me to add P outside of this subproof. Why am I doing that? Because I don't have anything, again, that I can break this up with, so I need a way to get some assumptions on the ground and maybe prove P if and only if Q so that I get this sentence and the negation in one that I can appeal to. So probably what's going to allow me to get the contradiction at whatever this line is to complete my indirect proof is going to be P if and only if Q again. I'm not sure, but that's my guess. And to do that, I'm going to need to try two biconditional introductions to introduce P if and only if Q again. So here's my guess about how this is going to work again. I'm hoping to get P if and only if Q and get a contradiction. So that means I need to assume Q, get P, assume P, get Q. Both of those will be by biconditional introduction assumptions. And I'll get this line by biconditional introduction. Well, by assuming P, I have not P at this line. That means that line 14 is going to be a contradiction. From a contradiction, we can infer anything at all because of the rule explosion. So we can infer Q at line 15. The other direction of this proof is, this subproof is going to work exactly the same way. So we're assuming Q at line 16. Q is got its negation, not Q, at line 11, so we can get a contradiction again. And once we infer a contradiction, explosion allows us to infer any sentence at all, so we can add P. Since we assume P and proved Q, assume Q and proved P, we can add P if and only if Q. By justifying it, that's lines 13 to 15 and lines 16 to 18. That line 19 that we just added, its negation appears at line 1. So that justifies this contradiction we were hoping for here at line 20. And since we assumed not P for an indirect proof, proved a contradiction, that allows us to prove P outside of this subproof at line 21. So that indirect proof subproof ran from line 12 to 20. And then since by indirect proof, after assuming not Q, we managed to prove P, we've got both directions of this biconditional in our conclusion. So we just have to fill in our justifications to complete the proof. So this completes the other direction of the provable equivalence proof. This happened to be a particularly tough example, but I thought it would be useful to use it as an example of some more strategies that you might pursue to get the sentences that you need in your conclusion, as well as an example of how to prove equivalence. Finally, we can prove that sentences are inconsistent. A proof shows that sentences of TFL are inconsistent if we can prove a contradiction from them. So we start by assuming each of the sentences in the set, and then step by step we should find some sentence and its negation along the way in our proof to show that assuming all of these sentences together leads to a contradiction. Unlike our example of provable equivalence, our example of provable inconsistency will turn out to be pretty straightforward. We have here a set of 4 sentences, and we have to show that they're inconsistent. So they are A or B, if A, then C, if B, then C, and not C. So I've written all of those out as our assumptions, and we'll show that they're inconsistent if we can prove a contradiction. So we need to find some sentence and its negation on this tree. Since we have a simple sentence not C, that is going to allow us to apply modus tollens to our assumptions at line 2 and 3, since we have the negation of the consequent of both of those sentences. Now we have not A and not B on our proof, both gotten by modus tollens. We've used assumptions 2, 3, and 4, but we haven't used the first one yet. That's a disjunction. There are two ways we can get rid of a disjunction. There's the disjunction elimination subproof rule, but we also now have disjunctive syllogism if we have the negation of either of these disjuncts. Well, we've actually got the negation of both disjuncts, so pick your favorite and use that to run disjunctive syllogism. So I chose to use the negation of B, and if we have the negation of this disjunct B, we can assume the other disjunct, A. So that's what I've added at line 7. And now we have A and not A both in the proof. So we're done. We can infer a contradiction. By proving a contradiction at line 8 from the sentence and its negation at lines 5 and 7, we have proved that these 4 sentences are inconsistent. And with that example, we've now covered all of the proofs and proof strategies we'll need to do within the natural deduction system. So you should know how to construct a proof in this system to show that an argument is valid, that a sentence is a theorem, that a pair of sentences are provably equivalent, and a set of sentences are provably inconsistent. And given that we've now added 5 new rules, you should be able to use your knowledge of these rules and the strategy we've covered to complete any proof in natural deduction.